I know it's starting. All right. You guys should all have this in front of you. Those of you watching, if you're watching this, not weird, nobody's watching it yet, but they will be one day. If you're watching, you need to download the Miss Pierce's study guide notes in the focus area introduction. You're going to need those to go along. Okay, everybody, first thing, after you've put it in, what should you put at the top? Because I'm going to ask you for it before you request a content assessment. Not your name, because it's in your notebook, so it should be yours. The what?
Date.
The date.
Yeah.
That's the most commonly forgotten thing on focus area notes. Nobody ever puts the date. Today is the 17th. Thank you. I have no idea what day it is. Okay. 17th. All right. This is not going to be all of the notes that you need to take this focus area. Okay. So I'm assuming that most of you have started studying this focus area already. I know we have 2 8th graders in the room. So for you guys will get to take it today, okay? But you may not pass it, and that's okay, because you might have to go back and do some more reviews. Does that make sense? Everyone else in the room, have you guys at least started studying this? Yeah, yes, Ms. Pierce, of course, because we did that playlist checklist in class together, right? Okay. So this is going to be a review of the information that's in your study guide, but it's broken down a little bit, and I'm going to talk about it a little differently, so hopefully it'll help you, all right? So we're going to get started. The first thing is we're going to talk about the building blocks of matter. So the first fill in the blank here is atoms. Okay, we're going to start off with atoms, which is the smallest unit of life. So it's the basic, this fill in the blank is building, the basic building blocks. Okay? What that means is that everything is made up of atoms. Okay, you are made up of atoms. The chair you're sitting on is made up of atoms. The paper that you're writing on and the graphite in it is all made up of atoms. It's what's around us. Even the air you're breathing is made up of atoms. Okay, they are the smallest form of matter that still has unique properties. Okay, you can split an atom into smaller pieces. Okay, that's what you guys know that because you've heard of the atom bomb, right? Okay, you can split an atom into smaller pieces, but once you do that, it loses its unique property. Okay, it's kind of like a Lego structure. You know when there's a big Lego thing that's built and it looks like a ship? When you take it apart, does it still look like a ship? No, because it just looks like Lego pieces. Okay, so atoms are like that. They have pieces that make them up, and when they're together, they perform a certain function. They act a certain way. But when you take those pieces apart, they no longer act that way. Does that make sense? Okay. So, if we have more than one atom together, we have something called an element. Okay, an element is more than one atom. So I'm going to draw, underneath here in this space, I'm going to draw some examples of atoms, okay? So this is what an atom looks like. It's got protons and neutrons, and then on the outside, it's got these little things called electrons that fly around the outside. This dotted line is kind of to show you that it's going around the outside. It's moving around the outside. But these are the actual electrons, the little dots. Okay. So that's an atom. Sometimes we write them like this. Okay, this little symbol is a symbol that lets you know what kind of atom it is. So that one is a nitrogen atom. Or I could do a hydrogen atom. Yes.
What would uranium
uranium, I think, is UR. I'm not going to drive this way because it's massive.
It's actually like 134.
Yeah, I don't know the exact number. It's way up there. Okay, so these are what atoms sometimes look like when we write them. Okay, does that make sense to everybody? All right, so if you have an element, you have more than one atom, but we're not going to mix the atoms. If we mix them together, that's getting different. So an element is going to be like if I had a bunch of hydrogen atoms all together. Okay. Notice they're all separate. They're not connected to each other, but they're all together in one spot. Okay. All right, now when we start putting atoms together, when we start bonding them to each other, we get something called a molecule. Molecule is 2 or more atoms put together. So you guys are really familiar with a few molecules, one of which you need to live, 2 of which you need to live. So here's one molecule that you're probably really familiar with. That's oxygen. Okay, 2 O atoms bonded together. Here's another one that you need to survive. It looks like Mickey Mouse. It's water. H2O. H2O. Okay? You can draw those. This kind of looks like googly eyes. Oxygen, water. Okay. Now, if we have more than one molecule, we have something called a compound. Okay. So if you had a bottle of water, there's some in the classroom, but not around nearby that I can see. That is a compound because you can see the water. That means there's more than just one molecule there because one molecule is way too small for anybody to see. Even with our best microscopes, we can't see that small. Okay. But you would have a bunch of different, I'm going to draw two Mickey Mouses here. Make sure they're actually touching so I know they're blended. Okay. So more than one is a mole. Does anybody have any questions for right now? Any questions for right now? So do you guys get the difference between a molecule and a compound and the difference between an atom and an element? Right. They're similar, but just one is more of than another. Okay, I'm going to scroll down. Is everybody good? Okay, so all of these things all these things that we just talked about, they're all pure substances. That should fill in the blank right there. Pure substances. I'll write it in a second. Okay, OCD people, did I get all the spots? Yeah? You're good? Okay.
Oh, I think there's one.
This is not, that's actually from above. Here, I'll scroll past it so you can't see it. Okay, these are all pure substances. Okay, no dumb is pure. Yeah, of course they're pure substances. All right, but it's important because if we mix them together, if we combine two different types of molecules or we combine an element with a molecule, we get something called a mixture, which once again seems like no dumb is Pierce. But think about it this way. When you breathe, what do you breathe? Oxygen. What else is in the air, though?
Hydrogen.
Hydrogen's in the air. What else is in the air?
Carbon dioxide.
Carbon dioxide's in the air. The biggest component of the air you actually breathe is nitrogen, believe it or not. Very little of what you actually breathe is the oxygen. So when you breathe, like to everybody take a big breath, you just breathed in a mixture. Okay, and when you breathed out a mixture because you breathed out a mixture of carbon dioxide and water vapor because that's what your cells are creating and need to go out. Yes?
You know what the percentage for nitrogen is?
I believe it's like 70%. Oxygen's only like 18% of our atmosphere. Huh? Probably a little higher, yeah. Okay, so why do we care? Well, when I was in college, I had to do this experiment where I walked into class and my professor handed me a jar and said, "What's in the jar?" And that was what we had to figure out. And we had to use what we knew about chemical properties to figure out what was inside that thing. So every single element has there's two different types of properties. Okay, there's physical properties and chemical properties. You guys already know this, right, because you studied your focus area. But the physical properties are how the molecule appears and how it behaves. And then the chemical properties are how it reacts, okay? So you can look at someone, everybody look at a person seated near you right now, okay? You can look at them and you can tell what they look like, okay? You can say what color their hair is, you can tell what color their eyes are, you can tell what color clothes they're wearing, you can tell how tall they are, okay? Could you tell how they would react to a scary movie just by looking at them?
Yes.
No, you couldn't. If you've never met them before, you could not know. Could you tell how they would react in a fight? If you got mad at them, could you tell how they would react? No, okay? So that's physical properties, how the substance appears and how it behaves, okay? There are different physical properties of humans than there are of chemicals, obviously. One of the ones, though, that you guys can know from humans and chemicals is color, right? Color's one. Now there are some other, there's a lot of them. I'm only going to list 3 of them. Does that make sense? Okay. Another one is something called malleability. Malleability. You guys say that with me. Ready? 1, 2, 3. Malleability. It's a weird word. Do you know what it means? Okay. If I tried to bend the leg of this chair, would I be able to do it?
Yes.
If you were really strong,
It's
then
really
Metal.
strong.
Maybe
Okay.
like the whole.
Yeah, this is a metal chair, right? Metal leg of the chair. What if I tried to bend aluminum foil?
Yes.
It's really easy, okay? That's malleability. It's the ability of something to be bent. It's a property of metals. If it's got higher malleability, it's much easier to bend that metal. You might want to write down there a little side note about what that means, ability to be bent. Okay, so you don't forget what that word means. Or you can put, I'm going to put bendability, which is not a very scientific word, but that helps me remember what this malleability means. Yeah.
Are dancers and ballerinas more malleable?
They're more flexible, but you couldn't pound them into a flat shape. Good question. Okay.
This is a Nazi picture.
Yeah, no. Malleability also, it's how well, if I were to take a hammer or something and mash it, is it going to flatten or will it stay its shape? Okay, that's mostly a property of metals. You're not going to get malleable air. You're going to get malleable iron or malleable copper. Okay. Another physical property. Who's got one? Yes. Texture. Texture's good. Okay. We don't usually measure texture though, so I'm going to add something else. If you wrote that down, hopefully you wrote it in pencil. Let's see. I'm going to say your state. State at room temperature. Okay, what do I mean state? I don't mean the state you live in. I mean the physical state. I mean gas, liquid, or solid. Okay, most atoms are solid at room temperature, meaning the temperature of this room right here. Okay. Some of them, like mercury, are liquid. Mercury, I think, there's 2, mercury and maybe bismuth, that are liquid at room temperature. And then there are some like oxygen, nitrogen, hydrogen that are gas at room temperature. Okay, that's a physical property of that atom. Now, chemical properties are how it reacts. So something like this might be, guess what? Reactivity. Okay, you can think of reactivity like how likely that atom is to get angry and fight with another atom. Okay, or if following our, your older sister gets a boyfriend and she breaks up with him and then gets together with another guy. Okay, reactivity is the likelihood that an atom is going to bond with something. How likely is it that the atom will react? Some atoms have a really high reactivity. Some of them react with water. You guys there's a video you can look up on YouTube about different atoms reacting with water, and they'll put about that much of it in a bathtub and it will blow the whole bathtub up because it's that reactive. There's atoms that you can't even get because it's illegal, because if it even touches the air, there's enough water in the air to make it react and burst into flame. Okay, so that's reactivity. Flammability. That's, what do you think?
the ability to burn.
Yeah, the chance that it's going to burst into flame. Okay? We have flammable chemicals in this classroom. Girls, you've probably used, gentlemen, you might have too, but acetone, nail polish remover, is very, very flammable. That's why you're not allowed to paint your nails on planes, in case you wondered. Because it's incredibly flammable, and if it even gets near heat, it can immediately catch fire. It also burns a lot colder, so it doesn't need a lot of heat for it to catch on fire, not like what's cool. Okay, the last one is solubility. Solubility is the ability to dissolve in something. Okay? So if you put sugar in your tea, it dissolves, right? What would happen if you put rocks in your tea? It would not dissolve, right? Yeah, break a tea, and it wouldn't dissolve. But there are different chemicals that dissolve in different things. If I drop sugar into oil, is it going to dissolve? Have you ever tried it? No. It doesn't dissolve in oil, but it dissolves in water. But there are some chemicals that when you drop them into oil, they dissolve in oil, but they don't dissolve in water. So that's a chemical property of those substances. Okay. Now, you can't see the very bottom part of this, so I'm sorry, but it should say if a substance has the same. So if a substance has a different physical attribute, okay, it could be different. Could be different or the same. So just because something is a different color doesn't necessarily mean that it's a different substance. Okay. It probably does, but it might not. Kind of depends. Okay. If a substance has a different chemical property, it's definitely a different thing. Now this is where it's cut off at the bottom of your page. If a substance has the same physical property, so you look at two substances and they have the exact same physical properties, they could be different or the same. That one's like 50-50. Okay. But if they have the same chemical properties, they're definitely the same. Okay. You can think of this like twins. So if they look the same, they might be the same person, but they might not. But if you look at their genetic makeup, they're definitely different people. Does that make sense? Or if you look at the way they react to things, the way that they act, they're definitely different people. Does that make sense? Okay. Does everybody have this, or any questions so far? Okay. I'm going to move down and erase. Is everyone good? Danny, you good?
No.
We're flipping to the next page, everybody. And we're almost done, so you'll get a chance to take your contents and stuff pretty soon. How are you guys feeling about it? Is this helping so far?
Yeah.
Okay, good. Okay. Danny, I'm going to scroll past it, but I'll leave the words down here so you keep going. Okay? All right, so now we've got this. The next page. This is a different states of matter. So at the bottom, we're going to put solid. Then this is going to be liquid. And this will be gas. Okay, and we're going in order of increasing energy. So as we go from a solid to a liquid, we have more energy. And a liquid to a gas, we have more energy. And this energy is usually in the form of heat. Okay, there's multiple different forms of energy. There's light, there's waves, there's, sound, I guess, is a form of waves. Light, waves, heat, motion. It's usually in the form of heat, sometimes in the form of motion. Okay, but if we're adding energy to a system, we're usually adding heat. We're increasing the temperature. Okay? All right. So a gas, or we'll start here. Solid has a fixed, so this is the shape column, so it has a fixed shape. That means it cannot change its shape. Okay, fixed means cannot be changed. Or isn't changed directly. Now, you can sometimes move solids, like this is a solid, but I can change its shape. But without touching it, it's not going to move. It's not going to change its shape. Okay? And I can't, unless I were to actually like tear this apart, I'm not going to change the shape of this towel. Okay, it's going to stay a square. I might be able to stretch it a little bit, but it's always going to go back to its same square type thing, even though it's kind of... Okay, and the volume is also fixed. It's not going to change its volume. It's not going to change how big, how much stuff is in, like how much space it takes up. Okay? Now, again, that's if it's not touched. So that's not going to, by itself, change how much space it takes up, unless something else moves it or changes it. Unless I add energy to that system by moving it. You are not going to change the amount of space that you take up unless you add energy to it by eating, or subtract energy by not eating. Right? Or you grow because you're growing. All right, liquid. The shape is not fixed. Okay, so we're going to skip over here to the volume. The volume in liquid is fixed. You cannot change the volume of a liquid, no matter how much you squeeze it, no matter how much you try to expand it. It's always going to take up the same amount of space, but the shape is going to fit the container. fit whatever container. So if I pour water into a cup, okay, if I were to pour rocks into a cup, are they going to change the shape of the rocks? Like, it's not going to melt to the bottom so that it fills in all the extra gaps, right? No, but if I pour a liquid in, it will do that. It will fill in all the gaps. There will be no air bubbles left by the time that liquid is fully seeped in. Does that make sense? Okay. Gas, it will also fit its container in terms of its shape, but the volume will expand to fit the container. Okay, so this is also fit container. Danny, are you done with this down here? At the very bottom. Are you done with this? Okay, this is important because they're going to ask you questions on your content assessment that say, a substance does this. What is it? Is it a gas, liquid, solid, plasma? Okay. It's worth mentioning, there is one above this, and it's called plasma. The only time you would have ever seen plasma is fire. Fire is plasma. It's beyond the gas. It's like if you superheat gas, you get plasma. Okay? Or if you look into the universe, but we don't have a lot of examples of plasma here on our Earth, because that would be very, very hot beyond what we can stand in terms of life. So the only plasma we know of is fire. And what happens if you stick your hand in fire? Bad stuff. Okay. All right. So now, what's this other arrow for? Here's the cool thing. When we add energy, that usually is in the form of adding heat. But there's this really cool property of gases and stuff where we can actually add two different things to get it to get things to move up or down. Okay. So if we add pressure, we can actually reverse this arrow, so it can go down like this. Okay, so that means if we squeeze things really, really small. Okay, that is how you make dry ice, by the way. You take carbon dioxide and you squeeze it until it freezes. Now, the opposite is true for the temperature. If we increase the temperature, it's going to take us up. Okay, this is another question. If you've taken a content assessment and you saw this question, you were probably like, what the heck is that? Has anybody taken a content assessment and seen this? Okay, so this is called a phase change diagram. It's a drawing, a graph that we use to explain how a phase changes for a certain chemical. Okay, this one is a water phase change diagram. You could have a phase change diagram for any chemical you want. Okay, they all have phase change diagrams, but water's the most common one because that's the one that we care about the most because it makes up most of our body and it does a lot of stuff. I'm going to make sure this is still recording because, hello, you're not. Oh, hello, are we still recording? Okay, we're still recording, I think. Good, awesome. All right, so, has everybody got this top part? Can I scroll past it so we can see this diagram? All right, so we've got, this is temperature in Celsius. This is E is for energy, so if you want to put that in there, E is for energy. Okay. So as the temperature goes up, the energy increases. And what we see happening is that we've got, as we increase the energy, so we're adding heat, you'll see, this is starting from ice down here, okay? So this point right here is ice. Nice. Now you'll see the ice, if you were to put a thermometer in the ice, you would see it start to raise in temperature, raise in temperature, raise in temperature. And there's going to come a certain point right here where some of it starts to change to liquid. That's when the ice starts to melt, and that's called the melting point, okay? But here's the crazy thing. The temperature of that ice is not going to change until all of the ice is melted, even though we're still adding energy. So let's say you put ice in a pot and you put it over the stove, okay? As long as the flame under the stove is going, you're adding energy to that system, but the temperature of that ice won't change until everything is changed into liquid. Once it's all liquid, right here, then it starts rising again. Okay, so at this point we are all water. All of it is water. Up until that point, from here to here, we have ice and water. Okay, because some of the ice, so imagine it like this, like if we were a block of ice, so we're all holding on to each other, and we wanted to go out the door, okay, would we be able to all walk through the door at once? No, but we have to stick together, so one of us can't get out the door and run away. We have to wait outside until everybody gets through the door, and then we can all keep moving towards the exit. That's the same thing that happens here, okay? Some of us are still inside the room, we're still ice, and some of us are outside the room, we're still water, but we're going to wait till everybody gets to the water phase before we keep going. Think like field trip when you were in 2nd grade, and you had to like stay with the teacher, and everybody had to wait for okay? Same thing happens here. This is where we get to the place where the water's gotten to its boiling point, where it's going to start switching to its gas phase. And for this point right here, you've got water and I've got steam or gas. Okay. Same thing. We've reached another door. Okay, we've reached the exit to the school, perhaps. All right. And now we all have to go through one at a time. Everybody has to switch to gas before we can all move on and start raising our temperature again. So this is no temperature change, but we're still changing phases. So I want you to tell me every place where water exists in this diagram. Which sections? Zach?
Technically all of them. All of them.
The liquid form of water.
B.
B, so you said B and C?
C.
Okay, what about D?
Yeah.
Still water there because we haven't been switching.
Yeah.
Okay, so all those three would have liquid water. Does that make sense, everybody? Okay. So I put this here, melting point and boiling point, so that you could write down what that is if you want to. The important thing to know is that melting point and boiling point, they are also chemical properties. There are other chemical properties of a substance. If a substance has the same boiling point as another substance, odds are it's the same exact thing. And that's one of the things that we use to determine what was in that soil jar. We use the melting point and boiling point of substances. We had a really cool little machine that you could zoom in on crystals and watch them melt, and then you take note of the temperature. It was actually kind of annoying because it took really long. You had to stare at crystals. You literally had to sit there with your eyes in this thing and watch the crystals slowly start to melt. It took like 20 minutes.
Melting diamonds.
Okay, everybody got this?
Mm-hmm.
Okay, so I'm going to stop the video and I'm going to give you guys a chance to take the content assessment. So these notes